Hi, welcome back to Book Club. And again, Book Club is all about like, go get this book, read it, listen to me. I'm going to kind of condense a bunch of chapters, maybe 1 to 2 chapters each episode in 20 minutes to just give you the high level view. And then really you reader, go read through and you'll have full understanding of what this material is, right? No need for a graduate class, no need for any of this stuff. These books are awesome, the ones I'm picking. And this is like sort of the Bible on rocket engines, and it's going to go all the way from like kind of the basic theory to like the no kidding how stuff is built. So I'm pretty excited to be doing this one. This is again one of my favorite books. And so last episode we kind of covered some of the basics, and again some of it wasn't basics. We were already starting to get into the real nitty gritty of what happens with regular rocket engines. And so in this one, we're actually now in chapter 4, as quick as this may seem. And in chapter 4, I appreciate this because it actually goes into a little bit of the flight mechanics. Now I'm going to do my best not to bastardize this drawing here, but assuming you have a rocket and then there's some wings and there's a rocket engine. Okay, great. All right, so now a couple things on this, and I'll try to use my different colors here well enough. And so this rocket is ascending, but it's at an angle, okay? And so gravity is still down. Earth is this way. Now thrust is going to be aligned along that axis. We talked about gimbal, so yet there will be a little bit of ability to gimbal that. You'd have to account for that gimbal. So the gimbal may adjust. Okay. If here's the horizon, okay, so that's horizon. Then this vector is actually the flight path angle, and so flight path angle there is theta, usually called theta. Okay, but then if you had a wing on here or whatever your kind of lifting body, there may be also, I'll put it different here. This is sort of the chord line of the wing. Then you would say the angle between the wing and the flight path angle. By the way, this is true for like an aircraft. Okay. That's alpha, so that would be angle of attack. Okay, and then the lift, which is going to be perpendicular to that wing, is going off of this direction. So there's lift. Okay, and then drag is going to be aligned with the flight direction drag. Okay, so usually when you do a very basic airplane, it's just thrust, weight, lift, drag, four corners. This is where you then get into a little bit more of the specifics, okay? And so the important part here in this chapter is they kind of walk you through, and I'm not going to go through all of the equations here, just because it's well done in the book. But the punchline is, once you account for all of this stuff, that drag and gravity losses usually are 5 to 10% of what you need to go all the way up into orbit. Okay, so not to be minimized. Now at Virgin Orbit, right, we were dropping a rocket off the wing of a 747, and so it was actually harder aerodynamics. We had to drop it, count to 5, start the engines, the rocket would pull up. There was a big pull-up maneuver. We had to have a little bit bigger flight surfaces. So, the point is, it was not easy, and there are loads associated with this. This is the forces. There are also like vibration loads and aeroacoustic loads that you got to deal with. Rockets are not the strongest of things, so they can also banana. This is really the start of making real rockets. You get into these details, and some of these things are, I'll just say, not easy. They're not impossible. They're just not easy. And what can happen a lot of times, we've been launching rockets for a while. A rocket that starts launching vertically and goes up, it might only have a, say, 3-degree angle of attack. And so the aerodynamics on a 3-degree angle of attack is actually pretty tame. And so, wind tunnel model, CFD are going to well account for what is really the flight dynamics of it. Again, back to Virgin Orbit, if you're doing something crazy, you're up to like a 30-degree angle of attack. Those aerodynamics are not easy. Go talk to anybody who's built fighter jets and things like that. And so this can, the full aerodynamic problem can go from, I'll call it medium to difficult, depending on your your architecture. Now, there are some people out there who still really believe in either single stage to orbit or let's go make this hypersonic engine. Here at Venus, we are making hypersonic engines. I can tell you almost right away that the math for scooping the air on your way to orbit doesn't really work out. There's a lot of details there, but it actually comes back to the systems level of equation of how big is that air engine and how long are you taking it. It's honestly, like, it's not, some people call it the Holy Grail. I don't see it happening anytime soon. Even though here at Venus, we're making this great sort of Mach 0 to Mach 6 engine, I don't really see that it's going to improve our lift capabilities to orbit. It's just all the rest of the things that go into a rocket. And we'll get into it as we get into these chambers, okay? And then, I mentioned a little bit about orbit dynamics and things like that. So this is also in chapter 4 as well, because it's getting into the nitty gritty. And so again, I'll just show you here, if this is Earth, I already mentioned, the space station sort of in the peach fuzz, but what you actually do, and I will exaggerate so you can see it, so not to scale, okay? And so let's say you started here, and your rocket went up and then over. And so actually what's happening now, let's say your burn is done here. This is now where you've second engine cut off and you've achieved orbital velocity, but what you've actually achieved is a parabola. And again, I'm exaggerating this, and this might have been too big of a circle. I'm going to regret it here in a second. So what happens at low Earth orbit at these speeds, 5 miles per second, an orbit is about 90 minutes. And so what's going to happen in 90 minutes if you don't do anything is your rocket is going to re-enter the atmosphere. Okay, so what you have to be able to do is 45 minutes later at the apogee, you actually have to have a second burn. And this is called a circularization burn. So you have to get up to here, add more energy, and apologies for I'm going to end up going over my nice beautiful diagram. This is how you then circularize, and now you're in low Earth orbit again, not to scale. This is true for everything that you're going to go do. And so if you're trying to put a satellite into geostationary orbit, which would be way out here, same sort of thing, you might get to low Earth orbit. Now you're in space, you could do it slowly. And so what, in fact, I'll try to do that here a little bit lower, because I do find this interesting as well. I'll do it here. So here's Earth. This time this will be closer to scale. And so let's say you start off in a low Earth orbit. And so what you would do, let's say you would do a first kick here. That would raise your orbit a little bit. Now you're not falling back to the Earth, you're already in orbit. So that would raise your orbit. And then you kick again, and then you would kick again, and then you would kick again, right? And then maybe you kick again. And now maybe this is actually where you would want to be at geo. And then, starting there, maybe I'll switch colors. Then you would kick here, such that instead of falling right back to where you were before, you fall a little higher. And then you would kick again, and you would fall higher, and kick again. And anyways, you get to the point where this whole thing is now circular, okay? So this is actually how you would transition up to geostationary orbit. Now, the reason I say it like this is at this point, you don't have to have a rocket engine. One of the reasons rocket engines, you really need high thrust. This whole thing has to happen in a couple of minutes. It's actually back to the drag penalty. If you try to fly through the air with a wimpier rocket, you're going to lose so much to drag and so much to gravity that instead of 5 to 10%, it gets way worse. And so, there's no one has made, say, an electric propulsion launch vehicle because the thrust is just not enough. One, you can't overcome any of this stuff. But once you're in the vacuum of space, a lot of this orbit raising can be done with a very either an electric engine, or honestly, it can still be done with the chemical energy, but maybe just that the engine's super tiny, and so it doesn't take a lot of weight. And so you have kind of a lot of these orbital transfer vehicles. That's what they're designed to do. Sort of have these tiny little engines that may still be driven with chemical rockets, but they're super tiny, so the weight of it isn't much. And again, if it takes you a couple days to sort of orbit raise, no big deal. Okay, it's worth it from that point of view. All right, and so the chess chapter gets, again, this is kind of starting the deeper details of flight mechanics, the deeper details of orbital mechanics, which really matter based on your mission. And then I think they even talk about some sort of interplanetary stuff that if you wanted to get into like how do you go to the moon, how do you go to Mars, let's start working through that. So pretty cool, okay? And then in chapter 5, which is where we're kind of headed next, we'll kind of get rid of this. Let me see what I have coming up. Yeah, got cycles coming up here. So we're going to get into pump cycles, okay? But really starting in chapter 5, I'll put it down here. This is now where we start talking about what are those fuel combinations, what is the oxidizer combinations. And we'll come back, I think I'll come back to this a little bit more in 7, but this starts off just talking about, and I'll draw a rocket. What's the best place to draw a rocket? Here. I'll draw it sideways, okay? And I'll try to sort of draw as many of these systems as you may think of, because ultimately this starts talking about systems. All right, so you have, say, a rocket engine on the back, doing its thing. As I mentioned, it's got a gimbal. Here's your second stage. You've got a rocket engine here, usually with a bigger nozzle. And then usually up front is your oxygen tank, because oxygen is heavier than the fuels. And this would be, again, say, an oxygen tank and a fuel tank. Okay, now what's happening as this rocket is burning, so gravity's down, let's say this ox tank is actually, here's the amount of liquid that's left. If you have this whole gap right there, something's got to fill that gap. Okay, so you also have to carry on board pressurant. So I'm going to add it here. Okay, and so usually pressurant is helium because it's light. And so a lot of times you'll have, at Virgin Orbit, we actually stuffed our helium bottle inside of the liquid oxygen tank. So it was cryogenic, so it kept the helium very, very dense. And then we would run a line down to the engine to warm up the helium, and then we would come back and insert helium both in the fuel tank and in the ox tank, so that you're kind of refilling those tanks, right? So as you're draining, you get a backfill. Otherwise, these get pressure locked and things like that. Like your turbo pumps are going to need some pressure. Okay, so you got to carry pressurant. Other things they talk about this in this chapter is safety. And while that might sound very simple, that includes things like isolation valves, where you can sort of isolate and do some maintenance, or main valve, secondary control of the systems. They're check valves. Okay. What you absolutely don't want to have happen sometimes is you want your oxygen fuel to go a certain direction, not others. So you have check valves, you have filters that have to be in those lines to make sure it's clean. Like a lock, you can't, for some reason, if you got some junk into your ox tank or your fuel tank, you can't have it go and plug up something in your engine. Your engine may melt and rip apart if you have all that stuff. So there's a lot that goes into there. Okay. If you're SpaceX and you're trying to do reuse, boy, a lot of gets into that in terms of reuse. Usually it's the engine cycles that drive the reuse. So how many reuses? So on a normal rocket engine, you would actually do, say, 20 reuses. And what that will let you do is build the engine. You may do 5 to 10 tests to tune the engine. Every engine flow path is a little bit different, so you are tuning to get that right O to F in terms of the highest performance. And then you want to make sure you have room to then go to orbit. Now, if you're SpaceX, you want that number to be 100, trying to drive it towards 1,000. So a lot of your design can change if your reuse numbers get a lot higher than that. Okay, there's control. A couple of different things. This diagram's getting crazy, so I'll just sort of mention it by words. But one is your performance. So here's ISP, and I'll draw it versus O to F. Okay, and so maybe you've got some curve like that, and you actually want to have this very specific O to F. That's what you've designed it for. That's what you do a couple of tweaks. Well, once you start flying, you may not know what's actually happening there. And so maybe you need to detect it. Maybe you actually, during flight, you started backing off and sliding to over here. Like, well, that doesn't work. And so you need some sort of control system to be able to divert more, in this case, more aux back up to here. Okay? So that would be for ISP point of view. But there's also thing called propellant utilization. You want to make sure you use all of your propellant. So you're going to have some sort of liquid line measurement, which can be hard because they can be massive. And so that you want to make sure you're draining all of your propellant. And again, back to maybe this curve, it actually on some logic, it might be, well, maybe it's better to go over here to drain it. For some reason, if you're draining slowly or you had a misload. So there's all the stuff that gets into control, not to mention just sort of the operation of the engine, like from a go command and turn these valves and, send telemetry and things like that. Okay. So there's a lot that starts getting into just even these engine systems. And then that's what I'm going to kind of finish here with a bunch of then cycles. So you have here your fuel tank and oxygen tank, and these are all beautiful pictures from Everyday Astronaut. And you have to have a pressurant. So a very simple rocket would just have maybe this helium be at high pressure. That works for very, very simple rockets. Otherwise, this helium is just at a blanket pressure, which is kind of filling the black space here. And then you have a turbo pump. So in an open cycle, if you follow this line, you're taking a little bit of fuel and a little bit of oxygen. You're doing a side reaction, usually called a gas generator, and that is then driving a turbine. That turbine is attached to a mechanical shaft, and you have an aux pump and a fuel pump running off of that same shaft. And so that's gas generator. You can have separate shafts. You could have one gas generator feeding two turbines, a couple different variations of this, but it's an open cycle because then this stuff is actually just sent overboard. Now, this is very simple. You can adjust the flow rates here to adjust your power, which gives you adjustment to the pressure. But what's important here, you actually have to recognize there's the ISP coming out of your rocket engine, right? This is the velocity. Back to that mass flow rate of the rocket is the negative the mass flow rate of the engine. Well, in this case, it's not. The mass flow rate of the rocket, there's about usually 2 to 3% that's just sort of dumping overboard. And so there is an effective ISP loss. Your ISP here might be great, but it's about 3% lower at a system level because of this design. But it's simple. A lot of companies, Virgin Orbit did, SpaceX did at the very beginning. Now, the aux-rich closed cycle, this is, the Russians did it. I think Ursa Major's now done, a couple of people are doing it. And what you're doing here is now you take a little bit of fuel, right? That's this line here. And you take all of the oxygen, so the entire balloon line. And what you're doing here is a little small side reaction. And so this really cold liquid oxygen has now become, when it's pressurized and heated from this little side reaction, so it's actually super critical, but still kind of cool-ish. And you're going to go drive this turbine, and which will drive the pumps of both. But this is done at a very high pressure. So let's say your engine is actually at 4,000 psi. This is done at like 6,000 psi. Such that all the exhaust of this now very warm oxygen with a little bit of combustion products in it then comes in and enters the rocket engine and then reacts with all the rest of the fuel. So aux-rich stage is closed cycle. You are not dumping anything overboard, so it's actually more efficient. Not only that, you can get to some pretty high pressures with it. Now this is a simple diagram of this. Actually, the bootstrap and startup of all this is pretty crazy. Okay, and this is called a pre-combustor. Okay. Then you have sort of the combination of all of these. I know my words are kind of getting in the way, but it's just over the tanks. This is now full flow stage combustion. So what the Raptor engine is. A couple of companies are now trying to do it. It's basically just the same thing times 2, where same thing, you're taking a little bit of fuel to react with all of the oxygen to go in here, but you're taking a little bit of oxygen to react with all the fuel to come in here. Now, why is this important? One, you see the turbine and the pump here is basically all in the fuel line, and the turbine and the pump here is all in the aux line. If I go back here, one of the biggest worries from a safety point of view is actually right here. So you have a shaft connecting two things, which there's possibly a leakage path. So between here, it's called your interpropellant seal in the moving part, but a big failure mode is if you get a little bit of oxygen entering over here into a little bit of fuel, there's enough heat through this kind of spinning parts, you can create a reaction and basically blow up your engine right here. So full flow stage combustion really minimizes that risk, and so it's a pretty awesome process. Okay, so that one's pretty slick. Tap off cycle, Firefly does this. This is where actually the way you believe the way Firefly does it is actually film cooling. We'll talk about cooling of the thrust engine, but what they're doing is actually using some of the fuel to sort of cool the edges. And so what you have happening here on the edges is you actually have a fuel-rich combustion. And because it's fuel-rich, it's actually cooler. And so you can actually then just have tap off. Now this high stuff is going to come and drive the cycle and go. So it's a kind of a cheat, not a cheat, it's a neat way. It's basically almost the same thing as a gas generator. But what it lets you do is actually not have to do regen cooling on this one. That's the tap off cycle. That one's pretty neat. And then the expander cycle. A lot of times you see this on upper stage engines. And we'll talk about the limit behind it. But you have the fuel that is being warmed up as you're sort of cooling the rocket engine. And so this fuel is now, usually this is done with like a hydrogen engine, something like that. Or you can do it with a methane engine. This fuel is now hot and gaseous, and it's at high pressure because of this pump. And so then it's then driving the turbine, which is driving both pumps and then coming in. So it's an expander cycle. So it's actually a really, really efficient way to do it as well. There's no side reactions. You're just basically taking advantage of the heat transfer, which you need to do to sort of keep this engine cold. And I think one of these next chapters will actually get into regen cooling. Basically, a rocket engine is like keeping a fire in a wax fireplace. You got to keep cooling the wax to keep the thing from melting. So a lot of awesome cycles out there. Different pros and cons, of course, different expenses, different timelines to get all of them working, and really that sort of gets into the kind of the nitty-gritty details. So this is great. This is great 2 chapters. I was kind of chapter 4 on the little bit more nitty-gritty details of flight as well as orbital mechanics, and then chapter 5 starting to get into the nitty-gritty details of what does it take to actually make not just a rocket engine, but all the rest of the systems, which would include the pressure and any safety things, and then the pumps. That's why we then looked at all of these cycles. So some good stuff. Again, if you have any questions, ask them below in the questions. This is my wheelhouse. I love doing it. Otherwise, dear reader, make sure this book club, go read it, dive in, and we'll see you next time on Book Club.